Uh, are you gonna like write on the on the screen, or how is it?
Yeah, I'm gonna write directly on the PowerPoint, and then
Oh,
yeah, so you'll be able to see my writing.
okay, and would you be like uploading like the final PowerPoint or no?
Yeah, I'm gonna upload. I can upload the PowerPoint, but I'm also gonna upload the presentation, like the recording of the whole thing. So,
Okay, okay, thank you.
but yeah, I'll talk to Dr. Bassel about uploading the PowerPoint too. All right. Well, I guess I'll go ahead and get started. So my name's Devin. For if you came in late, I'm Devin. So basically, I'm just going to work through some problems, and I'm going to put I guess, the PowerPoint, the recorded uh, tutorial session onto Canvas, so you guys can see it later if you want to, and just like interrupt me, ask questions, whatever. Yeah, if I'm going too slow, too fast, just let me know. Um, and so I figured that this is just a good way to learn and practice problems doing it together. So, all right. So I've got 5 problems. I'll try to do like 10, 15-ish minutes per problem. Um, so usually I try to do like I don't know how y'all have learned solving problems, but I used to do like a given find solution type of methodology. Um, so uh, I'll read through it first because that's just what I do whenever I'm working problems. So for low speed laminar steady flow through a circular pipe, shown in the figure below, the velocity u varies with radius and takes the form, that equation there, and where mu is the fluid viscosity and delta p is the pressure drop from entrance to exit. So what are the dimensions of the constant b? So usually I'll read it once through just to give myself a chance to like absorb the details, and then I'll go through the give and find solution process of like outlining what I'm looking for. So let me get my pen working quick. All right. So for the givens, I think probably a good thing to note is that it's low speed laminar. So I'm gonna write that. And it's also, because it's low speed, it's incompressible flow. That may not be super useful now, but for the future, low speed flow is incompressible. So that's just a good note to put. And it also says that it is steady flow. So we're not looking at any sort of like time dependent transient flow, anything like that. And then it tells us that we have a velocity u that varies with radius. So that's good to write that down, that we have that dependency there. So then we have this equation that says that u is equal to b delta p over mu times rho naught squared minus r squared, or not rho, sorry, r naught squared minus r squared. And then it looks like that's pretty much all the givens we have. So for find, it just wants us to figure out what are the dimensions of B. Okay. So solution. Oops. So for solution, I guess so this type of problem, some people call it like dimensional analysis, even though it's different than the dimensional analysis that we've always done in chemistry, that kind of thing. So the way that I do it is I just go through and write the dimensional quantity, like meters or seconds or whatever, for each of these. You could also write it. Some professors will do like, they'll, instead of meters, they'll write length, and instead of like area, they'll write length squared. So you could do it either way. but I'll write it in terms of actual units. So for velocity, on the left-hand side, let me do this. I'll start down here. So for velocity, we would have meters per second, and that's equal to B, what we're looking for, times this delta P quantity, which is going to be pressure is newtons per meter squared, right? So would have newtons per meter squared divided by our viscosity, which is a kilogram meter per second, or kilogram over meters times seconds, I should say. And then we're going to have that multiplied by this R naught squared minus R naught, which that whole subtraction is going to be a meter squared term. Hey, come on in. No, you're good. I'm Devin. Yeah, nice to meet you too. So we're just starting problem one. So basically, I wrote the givens and then what we're looking for, which is the dimensions of the constant b, or not whatever b is. We're looking for those dimensions. And so right now, I'm just writing out the dimensions of like each of those quantities, and then we'll start working it from there. Okay, so from here, now that we've listed all of the dimensions, I'm going to start like combining, canceling, doing that sort of thing. So we can cancel meters squared with meters squared. We can cancel this meters with this meters. And I'll probably leave it there for right now because I don't see anything else that's like obvious. So if we go to the right side, we'll have 1 over seconds is equal to B newtons. The seconds that was in the denominator can come up. So we have newtons times seconds. And then kilograms underneath that. And then looks like that's where we're at. So from here, what I would do is recognize that a newton has a bunch of dimensions locked up inside of it. So we can split that newton up into kilogram meter per second squared. And then that is multiplied by seconds. And that's divided by kilograms. Oh, it has a built-in eraser. I keep hitting on accident and erasing my own stuff. Okay, so then from that point, we can go ahead and cancel we can cancel one of the second terms with the second that's next to it. And then we can cancel the kilogram with the kilogram. And we can also cancel this second with this second. Yeah, so that's going to leave us with 1 is equal to B times meters, which would then, if you just divide the m over, meters over, you'll get 1 over meters equals B. So that's the dimensions of B is going to be 1 over meters. So any questions on that one? Cool. But say if you have any questions, just even if we're on the next problem, just interrupt me and we'll do that. So okay. There it goes. Okay, so problem 2. So we have this figure. It says the fluid's glycerin at 20 degrees Celsius, and the width between the plates is 6 millimeters. And we have so it's flowing to the right, and it has this flow profile, and it says what shear stress in pascals is required to move the upper plate at 5.5 meters per second. And then it wants to know what's the Reynolds number if L is taken to be the distance between the plates. So I'll go into my givens. I'll write them down here. Okay, so we know we have glycerin, 20 degrees Celsius. We have this width H between the plates, and it's 6 millimeters, but I'm going to write it in meters. And then it says, so then our find, it says it wants to know what our shear stress is if the top plate is moving at 5.5 meters per second. Okay. So I'm going to start the solution up here. Okay. Oh, that's only one of the finds. So the first one is it wants the shear, and then for the second quantity, it wants to know what the Reynolds number is. So Reynolds number, just a quick recap, is a dimensionless quantity, and it's based upon a characteristic length of your system. So in this case, it's telling us it wants us to use H for that characteristic length. Or it says L, but in this case, L is equal to H. So you could write maybe like RE sub L to signify that's your length you're basing it on. Or you could say maybe REH, since we know that's what the distance is in the figure. And I think, yeah, that's what I got a list. Okay. So to solve this, we're going to start by saying, okay, so we're looking for our shear. So we know a formula for shear, that's tau equals to, or shear is equal to your viscosity times your velocity profile, du dy, or in other words, the rate of change of your velocity as you move in the y direction. And so this du dy could be like, it could be exponential, it could be quadratic, maybe even cubic, or however it needs to be. But in this case, when we look at our figure, we see that it's a linear profile. So that makes things nice and easy. So since we have a linear profile, we can go ahead and rewrite that du dy as delta u over delta y. How's it going? So if we had like a quadratic profile, then you'd have to somehow get the like equation for that velocity profile, and then you could like take the derivative. But in our case, we'll just rewrite it as delta u over delta y. So then that can be rewritten as delta u is going to be the u at the plate. We'll just call it u sub p, u plate. And then we subtract out u, I'll call it uf for the fixed plate. And then we'll divide that by yp, y at the plate, minus yf, y fixed. And then the reason I did that is just because, so I don't skip a step, because then the next step will be to write, to note that uf and, here I'll write it down. So maybe we could say note uf and yf both equal to 0, because we're defining 0 as the plate in the y direction right here. Oops, right there. And it also says that U is equal to 0 there because it's fixed. So I'll write that on here. Okay. So if those are both 0, then we can rewrite our tau expression as our shear expression as viscosity times UP over YP. And then, so then we might say, okay, well, we know UP. UP is the condition it gave for the movement of the plate. That's going to be 5.5 meters per second. And then YP is H. This is that 0.006 meters or 6 millimeters that it gave. And then the only thing left is this mu quantity. So we might say, what's that? So what Dr. Vassal has done is that he provided this table on a canvas. So this is just table 1.4. So, so if you need it, you can find it there. But if we look at this and we find glycerin, since it's stated glycerin's the material we're working with, then it says that mu for glycerin is 1.49 kilograms per meter second. So I'll go back here and say that this is 1.49 kilograms per meter second. And then now we know everything. So we can just say that shear is equal to our viscosity. Whoops. I need to take my hand away from this button. That's equal to 1.49 kilograms per meter second. And then that's multiplied by our 5.5 meters per second divided by 0.006 meters. And then one note I will make here is that I do try to write my units in every step of the problem, just because for me it keeps me like accountable as far as like if I copy something wrong and I'm going like, why are my units not working? Yeah. Then they'll usually like, the problem is supposed to be height, and you get like meters to the 6. Yeah, exactly. Then I'll be like, okay, I've done messed up somewhere. So so I just figured I'd mention that writing units is really good for keeping track of things. So yeah, so this will be equal to, let me see, 1.49 times. Okay, so this comes out to be 1365.833 kilograms per second squared meter. So now we're looking at that, and that is an answer, but it said it wants it in pascals specifically. So we need to figure out how to turn that into pascals. So I guess when we're looking at these units, the thing to note would to think about, okay, a pascal is a Newton per meter squared. So then is there some way that we could transform this into Newtons per meter squared? And so then we might say, okay, well, a kilogram meter per second squared is a Newton. So if we multiplied top and bottom by meters here, then we could turn that kilogram over second squared into Newtons by doing that. So I'm going to multiply here by meters over meters. And then that's going to give us 1365.8 3. I'll do this. So this quantity here, kilogram meter per second squared, that is a Newton. So then this would be newtons per meter squared. And then that is a Pascal. All right.
If we know that like kilogram over second squared meter is a Pascal, would we need to like show that we're
No. If you know that that's a Pascal, then I'd say you could just write it. Yeah. But that's how my mind works, is like seeing that and then just writing it out. But yeah, I'd say you could just go straight there.
And then just another question real quick. So like obviously if this is like quadratic or like cubic, like you pretty much would just derivate and then like once you got to the same point, you just follow the same process. So it just makes it longer.
Yeah. So if for some reason we had like a some sort of quadratic profile, which if you were doing like research, let's say, then you might have like some data and you'd have to like do a curve fit to the data and get some sort of equation. And then you could derive the equation to get that du dy value.
Gotcha.
Yeah.
And then just follow the same process.
Right.
After that. Okay.
Exactly. Yeah. So
in that case, wouldn't then tau depend on some other variable?
yeah, I mean, I guess in this example, because it's like one-dimensional flow, it simplifies things. But if you had like some sort of flow that was real world, then it would be like three-dimensional. So you might have to derive with respect to x, y, and z, and then that's why we have like ANSYS Fluent, because it does this for us. So, but yeah, because that you get into, once you do that, you'll get into like the Navier-Stokes equations, and they're actually not solvable unless you use an iterative method.
That's
Okay.
stuff.
Yeah, it's wild. That's what CFD and like ANSYS, that's like the whole purpose of Fluent, is just solving the Navier-Stokes equations. So yeah, okay. Are there any other questions online or in person? All right. Well, I will go ahead and go to number 3. So, and again, that table's on Canvas if you need it. Yeah. Oh, you were so right. I completely just was about to skip half the problem. Thank you. Okay, so that was my bad. Okay, so part B, it wants the Reynolds number. So Reynolds number is defined as rho times velocity times a characteristic length, which in this case, I'm going to write L for that, over mu. And so just a side note, that Reynolds number, you might also see it expressed the d for diameter. So that'd be rho v d over mu. And that would be like for a pipe flow or something like that. So that's just a note. If you see it like expressed like that, that's probably because you're referencing a pipe flow versus like some sort of just plate flow or whatnot. And then, like I said, you could also write this as Reynolds number with an h, since it specifically says that that L distance is h in this case. And so that would be equal to rho vh over mu. And also mention real quick too that this is just the way I write things, but I write v for velocity because every person does this different. But if I do volume, I do v with a bar through it. And then for like the kinematic viscosity, I do nu. So that's just so that if you see me write different v's, that's what they mean. Okay. So for Reynolds number, we can just go and plug in our values. So rho is going to be a value from table 1.4 again. So both our viscosity and our rho, our density, are going to be table 1.4. And then we have V and we have H. So I'll go over here. So the viscosity is 1.49 and the density is here, 1260. So if we write this out, we'll get 1260 kilograms per meter cubed times our velocity, which is 5.5 meters per second. And our H is 0.006. And then our viscosity is 1.49. Okay, so if we cancel our units, we can cancel kilogram with kilogram. We can cancel these, all three of these meters cancel that meter cubed, and then seconds with seconds. So Reynolds number should always be dimensionless. So that's a good check to make sure you've done it right if you get a dimensionless Reynolds number. And that is going to equal to 27.906. So as a reference, Reynolds numbers that are low like this, if you're getting Reynolds numbers in like the thousands, that kind of thing, then that's indicative of like turbulent flow. So the higher Reynolds number, the more like chaotic your fluid motion is. And so 27 is a pretty low Reynolds number. And so that means that you have laminar flow. And so since the problem stated that it was laminar, this is that's just a good check. Being like you expected laminar type Reynolds number, so it matches up.
Would this equation even work if it wasn't laminar? Because I know, like, obviously, like when it's not laminar, that means it can be compressible, right? Which means that density can change.
Right.
So, like, would this equation even be applicable? Would we have to just like approach it entirely like differently, or would we be able to like derivate this equation with respect to time, or like how do you go about that?
That's a good question. My understanding is it's still applicable even in supersonic flow.
Okay.
But you're right that supersonic flow gets weird. And so your density would change. So I suppose if you were going supersonic, then you would have to know what the density is at.
So it'd just be like if you're doing supersonic, it would be for like a specific point in time. You couldn't do it for like the entire thing.
I think so. But what I'll do is I will ask Dr. Bassel just to make sure. Yeah, I haven't done that much supersonic flow myself, so let me put a little note on here. I'm going to ask him about that.
What range of Reynolds numbers is it like? I guess where is the transition from like laminar to turbulent, or where is it like questionable whether it is or not?
Yeah, so there's like a laminar regime, and then there's a transition regime, and then there's your like supersonic compressible type regime. I guess compressible is a good way to think about that, or turbulent regime. I mean, so I believe that the transition's around 2,000 to 3,000, somewhere in that range. Yeah, so I could write like a little. So if we have like laminar, and then transition, and then turbulent is what I meant to say earlier. Then I believe if this is 0, and then this is going off towards infinity, then I think somewhere around the 2,000 to 3,000 mark, somewhere in there. But I will check on that as well, just to make sure I'm telling you right. And then Let's see. Okay. Let me write it this way. So basically, you were wondering, in supersonic flow, does anything change?
Oh, sorry.
No, you're good. You're good.
Yeah, pretty much. I mean, like, just as far as what this equation goes, just because I know he was saying in class that like density changes with supersonic flow. So
Yeah, for sure, for sure. Alrighty. So I will definitely ask him that for sure.
Real
Yeah.
application, is it actually a good idea to sometimes purposely make sure your flow becomes turbulent, transition, laminar?
I guess like ultimately laminar is usually more desirable.
I mean, it doesn't really
Because-
exist much though, right? Like
Right.
linear flow is like really hard to achieve, isn't it?
It is, yeah, yeah. Laminar flows really hard because once you get into turbulent flows, there's so much like chaos going on that you have to start. You have like these eddies and vortices in your flow, and then if you're doing like a simulation or something like that, you have to have a model that's going to calculate what all of that chaos is. So like some things like if you're mixing something, like let's say in like a hot water tank, and you want to mix the cold water and hot water the most effectively, then you want turbulent flow because just like mixing a cup of coffee, like sugar into coffee, it's going to improve the mixing process. But if you're actually trying to like do calculations, then it's going to make it a lot harder to do the calculations. Yeah. Does that answer your question, kind of? Okay, cool. Okay. So alrighty. Any more questions on that one? No. Well, there it is. Okay, so problem 3. All right, so now we have a block of weight W that's sliding down an inclined plane while there's a thin film of oil that is between the block and this plane, and like in the figure. And then that film has a contact area of A, and its thickness is H. So if we're assuming a linear velocity distribution, like in the other problem, then in that film layer, then we want to derive an expression for the terminal velocity of the block, which we'll call V. And by terminal velocity, what it means is a velocity with 0 acceleration. So constant velocity, you might say. Okay, so for my givens, I might say, okay, we have this weight W, and then we have this inclined plane. I'm going to draw a little picture right here. So we have our block, and we have this plane, and this is that film of oil that is between the block and the plane. And in that film, there is a, there is a velocity distribution, like so. So kind of like the other problem, we have this velocity distribution in that oil. Okay, and then we know that the film has an area A and the thickness H. And we have the linear du dy. And then for our find, we just want to know an expression for V. And I'll put a little note here. This is terminal velocity, or acceleration is 0. So okay, so the way that I worked this is a good place to start is to do a force balance on the block. So if we want to say that our coordinate system is aligned with the plane like this, where this is our x direction, this is our y direction, then we could say some forces in the x direction equal to 0, because we have 0. Or let me do it this way. We could say some forces in the x direction is equal to max, but since our acceleration is 0, then we're going to get just 0 there. So then, if we're thinking about, okay, what all forces are on this? Well, we know we have our weight that's pulling directly downwards. And then that shear in that that lubricant, the oil, is going to be like having a friction force on the bottom of this block as it slides. So we're going to have a force going back against the motion, and that is going to be caused because of our shear. But shear is it's a stress, right? So it's newtons per meter squared. So we have to have shear times an area in order to have that be in force units.
And then just a quick question. Are
Yeah.
we gonna get to a point in the class where like buoyant forces will matter with this? Or is that not something that like fluid dynamics goes into?
No, you'll do buoyant forces. Okay. Yeah. So I guess with buoyant forces, that would be more if you have something submerged in the liquid.
It's like so small here that the film is so small, it's just negligible pretty much.
Yeah, that would, yeah, I think so. Yeah. So for buoyant forces, I guess you would have something fully or partially submerged. Whereas I see what you're saying, because if there's film, then it's gonna be weighing down, right? So yeah, I'd say here it's just assumed negligible. Yeah. That's a good point. So okay, so we have our force balance. F of x is equal to, or Fx is equal to 0. So what we can do here is say, okay, so what are our x forces, like we just discussed? So we're going to have some component of our weight in the x direction, and then we're going to subtract from that our shear times area, because it's going in the opposite direction. And then that's going to be equal to 0. So we know that shear is going to be equal to our viscosity times our velocity profile. So we can rewrite the equation like that.
Friction force is shear times area.
Mm-hmm. Yeah, so the way that I was thinking about it is that, so as the block is sliding down the plane, the oil is going to be, that shear force is going to be between the top surface of the oil and the bottom of that box. And so because the block is sitting on the oil, then as it's moving across the top surface of the oil, there's that shear interaction between the two.
You don't account for normal force, do we?
No, because we're just analyzing the block here. So your normal force would be equal to the in this case, the y component of your weight. But since we're just summing in the x direction, then we're not accounting for any y direction forces. So, okay, so where do we go from here? Okay, so if we look at the picture there, we see it provides us the angle theta. So I'm going to draw a little picture again, so it's easier to see. Okay, so we have our block. We have this angle theta. And our weight is like this. So this is where imagining these angles is good. So we can say, okay, we're going to have a component of our weight in the x direction. That's Wx. We're going to have a component in the y direction. That's Wy. And so if you look at these angles, then this angle right here is going to be theta as well. And so if we know that that's theta, and we know that sine is going to be your opposite of your hypotenuse, then your sine theta is going to be equal to W, or that's my bad. Oh yeah, here we go. Wx over W, or in other words, Wx is going to be equal to W sine theta. So that's an important quantity to note. And then the shear force, like I said, is going to be the mu du dy. So for Wx, we'll write W sine of theta, and we'll subtract mu. And then just like the previous problem, we can write that du dy as delta u over delta y, because it's linear, times a equals 0. This is linear. Okay. So then what we can say is that W sine of theta minus mu times, I'm going to rewrite that delta u as the velocity of the block, as the max velocity, the top velocity. So that's v minus 0 at the plate, and that's because we're assuming no slip condition at the plate. So there's no velocity at the plate surface. And then on the bottom, we're going to have our y. So this is going to be h, the thickness of our film, minus 0 at the plate surface. And then times a equals to 0. Okay. Okay, so with that in mind, I'm going to rewrite it right here real quick. There's v over h times a equals to 0. And then what we can do is rearrange this for v. So we could say bring your shear term over to the right-hand side. And then solve for v. So we have v is equal to W sine theta multiplied by h. And I'll do that to make it a little bit more clear. and then divide by A and divide by viscosity. And that is your answer to that one. So if they gave you values, then of course you could plug in and find it, but
I'm still just a little confused at understanding conceptually how we can substitute friction for tau A.
sure,
So,
yeah.
So that's saying that essentially the shear stress in that fluid is only due to the friction from the block sliding down it. But if there were other forces contributing to that shear stress, wouldn't that? Yeah, I guess I'm just having trouble conceptualizing.
Yeah, sure. So, okay, let's see. So if we have our block here again, and then we have our plate, and then I'm just gonna say our film of oil is this dashed box here. So I guess
a better way to help phrase my confusion is why doesn't the weight affect the shear stress in the liquid?
oh, okay. So why doesn't the weight affect the shear stress?
Because if there were like something say pulling the block,
Right.
then in my mind we couldn't necessarily say that friction is tau alpha because or tau area because tau would be a lot more than just the friction force would also be pulling.
Right. Okay.
I think this question, Loki, just assumes a lot of stuff.
Yeah,
Like,
yeah.
It's just like,
Yeah.
just like, the way I'm looking at it is this is like a baby question to get us
Okay.
introduced to fluid dynamics. So it's like, all right, or fluid system. So it's like, all right, let's take everything that would make this work.
Okay, I see that.
Yeah. No, you make a good point. You make a really good point. Yeah. So to be honest with you, I don't know that. Yeah, I don't know the answer to that. So, but
That makes me feel better because if you don't know, that means we don't have to.
Yeah.
right. Yeah.
You don't have to worry about it.
Right. Exactly. Yeah.
You got a strap. This bridge doesn't only
Yeah.
This exam and make it exactly like the actual. Switch out the numbers. Undergrad street.
I guess if you were thinking about friction, then the lubricant would change your friction coefficient, right? And then you could use the y component of the weight to calculate your right. Exactly. Yeah. So, yeah, I'll ask him. It could just be that it's so small that it doesn't really matter, but I will ask him to make sure about that. Yeah. And then the question you had asked me earlier about the buoyant force, yes. I figure I might as well ask him that too.
I'm sure it's just like small enough to where it's like negligible. Like it's gonna still be making contact with the block itself.
Yeah, exactly. I have no idea if I spelled that right. No, you're asking good questions. Yeah, and I'm curious now, so I'll definitely run this by him. I was trying to take notes as I go. That way, I remember this tomorrow. All right. Okay, so that's table 1.4 again. So like if you were looking for that viscosity in that expression, you go back to table 1.4. All right. Any questions online? That just let me know if there are. All right. So problem 4. Okay, so a thin plate is separated from two fixed plates by very viscous liquids mu1 and mu2, respectively. The plate spacings H1, H2 are unequal, and the contact area between the center plate and each fluid is A. So if we again assume linear velocity distribution in the in each fluid, then we want to derive the force F required to pull the plate at velocity V, and we want to determine if there's a necessary relation between the two viscosities. So we have mu1 and mu2. We're running a little bit short on time, so I'm just going to write less words and just write symbols. So then we have H1 and H2 and A. And then we know we have a force F, velocity V. So our finds are going to be A, looking for F, and then B, is there a relationship between mu1 and mu2? Okay, so it says we have linear velocity profiles. So they would look something like this, just like before. And
It will be flipped, right? Because the velocity will be 0 at the fixed plates.
yep, you're right. You are right. I was thinking that the outside ones were moving. Yeah, good catch. So it looked like that. That was my bad. And then, okay, so we want to find F. So this one's going to be similar to the previous problem, where if we sum our forces in the x direction and set it equal to 0, then if we assume that our x direction is along with the motion of the plate, then we're going to have Fx equals to wait a second. Sorry, we have Fx minus the shear stresses like we had before. So we'll have area times shear 1 plus shear 2, because they're both going to be fighting the motion of the plate. And we're assuming that we have a constant velocity here. So that's why I put 0, because we have 0 acceleration. So say A equals 0. Note, okay. So then our Fx is just F. Our area is A. And then our tau 1 is going to be mu1 times our d du dy, and then plus mu2 times du dy equals to 0. And then we know that both of our velocity distributions are linear again. So we can rewrite this as mu1 times, this is v, our top term, v minus 0. Our bottom is going to be h1 minus 0 plus mu2. And again, the same velocity for both, but then this one's h2 minus 0. And then that's going to be in 2 parentheses there. That's going to equal to 0. So then F minus A times, this would be what? Mu1 V over H1 plus mu2 v over h2 equals 0. And then if you really wanted to, you could go ahead and pull that v out of there. So your final expression would be f minus a v, since the v is common, over mu1 over h1 plus mu2 over h2 equals to 0. So that's part A. Then part B, it says, is there a relationship between your viscosities? So the answer is no, there's not. And so if we're looking back at that image, it's kind of a weird question. It got me a little bit. I was like thinking about it.
Is it asking like if they're dependent on one another? Is that
Right, exactly.
In what scenario would you have two viscosities dependent on each other?
I have no idea.
I guess,
I have no idea.
I guess like maybe like if you had like a semi-permeable like plate in the middle, and then you had like the viscosities of each were like affecting one another. That could probably do it. But like,
Yeah.
that sounds like it's way out of our league. That's graduate level.
Yeah.
No, that's a good point. Like maybe if you had a plate, and then you had like viscosity 1, and then like maybe viscosity 2, like you had oil sitting on top of water.
Oh, like something different.
Maybe.
Yeah.
Yeah. So I don't know how they would be related in that case, but yeah, in this case, there's no relation. So right. There's a barrier separating them. So I can write here, barrier, no dependency on each other. Okay. So the last one's pretty quick, so I'll go through it real quick. So we have an airplane. It's flying at 555 miles an hour. So it's wondering at what altitude in a standard atmosphere will the Mach number be 0.8? So given will be velocity is equal to 555 miles per hour. And then I'll just say find. So it wants to know altitude. I'll say it's h. H is altitude. If Mach number is 0.8. So solution. All right, so we have two equations we're going to use. One is the Mach number equation, which to find Mach number, it is v over a, where a is the speed of sound at blank altitude. Okay, and then v is the velocity. So if we know we want a 0.8 Mach number, then, and we know our velocity is 555 miles per hour, divide that by a. So if we solve for a, then we're going to get a is equal to well, okay. I solved this. I changed the units to meters per second. So I'm just going to write the value in meters per second since we're short on time. But okay, cool.
I think they weren't exactly like that inquiry. Had us do it, and it wasn't bad.
Okay, good. So, okay. All right, so that's your V, and then if you plug your V in here, instead of having that miles per hour value, you'll get A is equal to 310.133 meters per second. And then if you use table A6, which is again on canvas. Then, and it's also, I put it there. If you look for 310.133, that is right. Wait, hold on. What have I done? Oh, for velocity. Here we go. You see it? Yeah, right here.
Like on a test and you doing interpolation right now.
He might make you do interpolation. I don't know. Yeah. What I had him for thermodynamics, there was a lot of interpolation, but for this class, he might just make it match up. I'm not really sure, but yeah,
So
I would.
Like 310.199.
Well, yeah. In this case, he just took the closest value. Whenever he was showing me what he did, he just took the closest value. So. All right. So then altitude is about that many meters. All right. So I guess that's all that he wanted me to cover tonight. So are there any other questions?
How do we do the homework? Yeah, that's a good question.
Well,
I'm a person that learns by examples.
yeah. Well, good. That's what this is for. So, I mean, if you have questions, feel free to email him or email me. Do you have, my email is at the beginning of this. I put it on there. So if you have a question, just let me know. Yeah. So, yeah, I'll go and shut this down, stop the recording. But I guess, yeah, we're done. So.
Thank you.
Yeah, no problem. Have a good one. Sure. I'm about to go do chest day right now. Yeah. You gonna do run? Bike? Yeah. Dude, I love spin class. Spin class is great.
Hot yoga.
Hot yoga, there you go. Have you done it before?
I've done hot yoga
Yeah.
before. It's actually not as bad as it's like the sauna, except you get to get stretched and
Mhm. I've done hot bar before. That's
Really?
really good. Yeah, they just have like these 3-pound, 2-pound weights, which sounds like it'd be really easy until the instructor has you like do a half squat like this for like 2 minutes.
everything
And
always sounds
everything
like
hurts. Yeah.
I just like woke up to 200 pounds and we were doing like calisthenics stuff yesterday and he was like, do push-ups and I got to like 27 and I was like, I'm gonna kill myself.
Well, yeah. Enjoy your workout. Thank you.
See you next week.
Yeah. See you next week.
Usually you could post like the recitation slides beforehand, if that's any
Yeah, like
possibility. Okay.
before the
Yes, I
recording.
have someone ask that. Can you relate?
Yeah. Oh, yes, I will. Yes. He was asking the same thing if I'll post the slides. Yeah.
Thank you so much.
Yeah. No
Have a good
problem.
night.
You too.
I'm gonna be here for a little bit longer. It's not a question. It's in the middle of something.
Yeah. Okay. Sure.